All right, universal gravitation and circular motion test review. Number 1, force of gravity is a blank force that acts over blank distances and blank other objects. Okay, compared to magnetic force or electrostatic force, gravity is a weak force. And gravity affects objects that are close together. It also affects objects that are really far apart. So gravity expands the entire length, distance of the universe. That is a very long distance. And gravity is an attractive force, meaning it pulls things towards itself, like the Earth attracts the moon. It pulls the moon down, it pulls us down. It does not push things away, or it does not repel. Number 2, the Earth was suddenly twice as massive. So we're increasing the mass. What's happening to the gravitational force? Well, if I increase the mass, then I increase the gravitational force. My gravitational force becomes greater, and that is said to be a direct relationship. So as a result, the gravitational force between two objects is directly proportional to the product of two masses. And we know it's the product because if I look at my gravitation equation, it says that Fg is equal to big G times m, all divided by distance squared. Okay, well, if I'm looking at the relationship between force and gravity, then, force and mass, if I look in between my two masses here in my equation, okay, they are being multiplied by each other. So the term that means the answer to two objects being multiplied by each other, or the answer to a multiplication problem, that is said to be the product. So because masses are being multiplied in my equation, then it's related to the product of those two masses. Number 4, if the moon was suddenly twice as far from the Earth, then the gravitational force between them would become weaker because there is a inverse relationship. So as the moon gets further away, so it's twice as far, then the gravitational force gets weaker. So the further two things are from each other, the weaker that force gets. That's an inverse relationship. So as a result, the gravitational force between two objects is inversely proportional to the distance squared. So how do we get the distance squared? Well, my equation says that the force of gravity is equal to big G times m divided by distance squared. So if we're comparing the force of gravity to the distance is in the denominator. So we're referring to the inverse of the distance squared. Distance is being squared, so it's the inverse of the distance squared. By what factor would the gravitational force change if two masses were half the distance they originally were? So if the distance between those is cut in half, and we just previously said that the relationship between force and distance was related to the inverse square. So my distance squared is the inverse. So if my distance is cut in half, so it's 0.5 squared. 1 over 0.5 squared is 0.25, which gives me 4. So it is 4 times greater when the distances are cut in half. Number 7, when a satellite triples its distance from Earth, the force due to gravity acting on it decreases. So in other words, as the distance gets further away, the force gets weaker. That's a decrease, and it decreases to 1/9 its original magnitude. And I know that if I know that my distance is my force is the inverse square, and my distance is now 3 times what it originally was, 3 squared is 9, which gives me 1/9. Okay, number 8, the diagram shows two objects with mass. So I'm looking at an object here, they both have masses represented by a capital M, and they are a certain distance apart. How much would the gravitational force if both their masses doubled and the distance between were cut in half? Well, force is directly related to the product of two masses. So if my masses are doubling, so one is going from 1 to 2, the other one is also doubled, then 2 times 2 is 4. And the distance between is cut in half. So the inverse square. So 0.5 squared is 1 over 0.25, which is also 4. 4 times 4 gives me a force that is 16 times greater, or 16 times stronger. And B, how much would the gravitational force change if both their masses doubled and the distance doubled? So if my mass is doubled, just like before, 2 times 2 is going to give me 4. And if my distance doubles, so 1 over 2 squared, which is 1 over 4. So 4 times a fourth gives me 1. So it's 1 times the original amount. Okay, so in other words, it is not changing. There's no change. Okay, number 9. The diagram shows two objects having a mass of 5 kilograms. They're placed 4 meters apart. So I have a mass here, mass A, mass B, both of which have a mass of 5 kilograms, and they are 4 meters apart. I want to know the magnitude of the gravitational force acting on each mass. So I'm trying to find Fg. Okay, well, Fg is equal to the gravitational constant times the mass, two masses, all divided by the distance squared. So Fg is equal to 6.67 times 10 to the negative 11 times my mass of 5 times my second mass of 5, all divided by the distance, which is 4 meters squared. Okay, when I calculate these, plug these all into my calculator, I get a force of 1.04 times 10 to the negative 10 newtons. Now, B is referring to the same situation. I still want to find the gravitational force, Fg, but my mass is increasing to 17.5. So one of the masses is getting larger. So same equation. Fg equals G times M divided by D squared. So force of gravity, big G is 6.67 times 10 to the negative 11 times one mass is staying at 5, the second mass is increasing to 17.5. And it's all divided by the same distance squared. Okay, after plugging this into my calculator, I get an answer of 3.65 times 10 to the negative 10 newtons. Okay, number 10. Referring to the diagram to the right. Okay, so what you see over here is a tennis ball rotating on a string. Here's my tennis ball. Here's the string connecting, and say this is the person's hand. Okay, so if this is the person's hand and that ball is swinging around a center, this is the center of the circle. This is the direction that it's going in, a counterclockwise direction. A is asking me to draw and label the arrow representing the direction of the acceleration. B wants me to draw an arrow representing the velocity. And C wants me to draw an arrow representing the force. Well, since I'm referring to a circle, okay, I'm referring to a circle, so acceleration in terms of a circle is centripetal. And centripetal means towards the center. So if I'm looking for the centripetal acceleration, then I'm looking for a direction towards the center. So here's my ball, here's the center. My arrow needs to go towards the center. And I'll label this A, C. Now B, let's skip B for a second. Let's look at C. C says draw and label an arrow that represents the direction of the force. Well, again, because my object is traveling in a center, or a circle, excuse me, this is a centripetal force. And centripetal means towards the center. So, back to my ball here. Here's my tennis ball. There's the center. I'll draw this in a different color. The direction of the force is also to the center. This is FC, centripetal force. Now, back to B. B is looking for the tangential or the linear velocity, meaning what direction does it want to go in a straight line? Well, that is always perpendicular to the force. If my force is traveling to the center, straight left from this position, then 90 degrees from that, following the direction that the ball is moving in a counterclockwise motion, it is going to be 90 degrees, it'll be straight up. That is the direction of the velocity at that position. Okay, now number 11, how does the rotational velocity compare between points A and B? So what you're seeing here are, let's say this is something circular. It could be a record, could be a CD, could be a frisbee. Here's point A, here's point B, here's the center. Okay, so as this object rotates in a counterclockwise direction, how does A and B compare in a rotational direction and in a linear direction? Okay, so rotational velocity and tangential or linear velocities. Well, rotationally, since both of these points are in a line, they're all in line with each other, it's easier to imagine that as they rotate, they will always be in a straight line. They will always be in line with each other. So the rotational velocities are the same. Okay, the rotational velocities do not change. It's their linear velocities that do. Okay, we'll talk about that here next. Linear velocity is a little bit different, and that differs because as objects move further away from the center, they have to cover more distance. So let me show you what I mean here. So if this is A, and I'm going to draw the path that A would take. It's just going to follow a simple circle like that. But B is going to follow a greater circle. The circumference is larger than A. Therefore, B has to cover more distance in the same amount of time. So because B has to cover more distance in the same amount of time, B has the greater linear or tangential velocity. So as objects or as points move further away from the center, they get faster. So as points move away from center, that leads to an increased velocity. Okay. Number 13, the diagram shows the position of a satellite as it orbits the Earth. So here's the Earth, here's the position of a satellite. So this little dot represents the satellite, and it's showing the positions as it moves in a clockwise direction. Okay? Circle the position of the satellite where it reaches the highest velocity. So we saw this in the digital lab. As the Earth in the lab moved closest to the sun, the amount of force acting on that Earth increased, and as a direct result, the velocity increased as well. So this satellite is going to have the highest velocity when it is closest to the Earth. So here's where it moves the fastest. Now, B says if gravity was turned off, at which position would the satellite collide with the moon? Draw and label a velocity vector. Okay, so remember that our velocity is always in 90 degrees to our force. It's going to move in a straight line. So if I was looking at this satellite right here, if gravity was turned off, it would fly in that direction. That one would not collide with the moon. If I was looking at this one right here, then if gravity was turned off, it's going to move in that direction. That one would not collide with the moon. If I was looking at the one next to that one, if gravity was turned off there, it would fall in some diagonal direction. That one would not collide with the moon. The only one that would collide with the moon was this one here on top. It's going to travel in a straight linear direction, and if I continue that arrow, it will eventually collide with the moon. Okay? So it would not be this one, it would not be this one, it would not be this one. It would be that one at the very top. Now, which law explains why the satellite would collide with the moon if gravity was turned off? Well, that is Newton's first law. It says that objects in motion will stay in motion, and that is the law of inertia. Okay, it's his first law. Law of inertia. So it's the object's inertia that keeps it moving after a gravity or a force is cut off or turned off. All right, so now let's look at some calculations here. We're talking about this ride. That's the rotor. It has a radius of 8 meters, so it's giving us some information here. It has a radius of 8 meters, and it takes 3 seconds to make 1 revolution. Okay, so radius, that is r. It takes 3 seconds to make 1 revolution. So it's telling me how long it takes to make 1 full turn. That is known as the period. That is capital T. Okay, so number 14 is asking me for the frequency of the ride. And frequency is the number of cycles per second, or also the inverse of the period. Okay? So if my period is 3, then frequency is the inverse of that. So it's 3 raised to the negative 1, or 1 divided by 3, and that gives me a frequency of 0.33 hertz. Number 15 is asking for the period. Well, we already determined the period. It was given to me directly in the question. The period, the time it takes to complete 1 revolution, that is 3 seconds. What is her tangential velocity? So I'm solving for V here. Well, if I look at what I know the know the period and I know the radius. Well, I can solve for velocity with the period and the radius using V equals 2 times pi times r, all divided by t. So 2 times pi times my radius, which was 8, all divided by the period, which is 3. When I multiply and divide those two, I get 16.76 meters per second. And the last one here, the centripetal acceleration, AC, is what I'm trying to solve for here. So there are a couple equations that have AC, but I need to look for the one that has the information that I already know. Well, I just solved for velocity, and I know the radius, so I can use AC equals V squared divided by R, where my velocity was 16.76 squared, divided by the radius, which was 8 meters. Okay, when I square the velocity and divide by the radius, I get an acceleration of 35.11 meters per second squared. All right, last page. So I have a diagram that's showing a toy plane traveling at a constant velocity in a horizontal circle of radius 1.5. The magnitude of the centripetal force of the plane is 6 newtons. So it is showing me a toy plane being held together by a string and it's traveling counterclockwise. It tells me the mass is 0.5 kilograms and the radius, the length of the string, is 1.5 meters. Okay? It also tells me the force, the centripetal force. Okay, so this is telling me centripetal force. Give me a second. There we go. This is FC. This is my radius, and this is mass. Okay, what is the velocity of the plane shown in the diagram? Okay, well, based off of everything I know, I cannot use 2 pi r divided by period because I do not know the period. But I do know, however, I do know the force, I know the mass, and I know the radius. So my equation would be centripetal force equals mass times velocity squared divided by r. So if I plug everything in, my centripetal force is 6 newtons. The mass of the toy plane is 0.5 kilograms. The velocity is unknown, all divided by the radius, which is 1.5. Okay, so I've got a typical problem that we've practiced here in class. I've got a fraction on the right. I need to make a fraction on the left, and I can cross multiply. So 6 times 1.5 gives me 9 equals, and 1 times everything that's up here is 0.5. The numerator does not change because it's multiplied by 1. So I get 0.5 times v squared. Well, there's a multiplication going on between 0.5 and v, so the opposite of multiply is to divide. So now I need to divide both sides by 0.5. And when I do that, this side cancels. And on my left, 9 divided by 0.5 gives me 18. And on the right, I have velocity squared. Now the last step is to get rid of that exponent. So I need to do the opposite, and that is to take the square root of both sides. When I do that, v is now all by itself. And the square root of 18 is 4.24 meters per second. Is my velocity. Now B is asking for the magnitude of the centripetal acceleration, so I want to solve for AC. Okay, well, I know the force, I know the mass. That's an easy one. I can solve for acceleration. So F equals ma. My force was 6, my mass was 0.5, and the acceleration is what I want to solve for. So there is a multiplication problem going on between 0.5 and a. So the opposite of multiply is to divide. And I divide both sides by 0.5. These cancel, and I get a all by itself. And 6 divided by 0.5 gives me 12 meters per second squared. Okay, number 19. In an experiment, a 0.75 kilogram mass is attached to a string. A student whirls a mass overhead in a circle with a radius of 1. The mass completes 10 revolutions in 10 seconds. So I know a couple things here. I know this is the mass. It tells me this is the radius. 10 revolutions in 10 seconds. It's telling me the number of cycles per second this is the frequency. Now I can simplify that. 10 divided by 10 is 1. So the frequency is 1 hertz, 1 cycle per second. So I know F. Determine the velocity of the mass. Okay, well, I've got the mass, I've got radius, I've got frequency. If I know the frequency, I know the period. They are inverses of each other. So if frequency is 1, then period is the inverse of 1, which is 1. So now I know the period. So now I can solve for velocity using v equals 2 pi r divided by period. So 2 times pi times my radius of 1 meter, all divided by the period of 1 second. So 2 times pi times 1, all divided by 1, gives me 6.28 meters per second. All right, and last one. What is the magnitude of the centripetal force? So I'm solving for Fc. Okay, well, I just solved for the velocity, so I can use that in an equation. And my centripetal force equation says mass times velocity squared, all divided by the radius. If I plug everything in, I know my force is unknown. I know that my mass is given to me, it's 0.75. I know the velocity, I just solved for it, is 6.28. Don't forget to square it, all divided by the radius, which we said was 1. Well, if I multiply 0.75 times the velocity squared and divide that by 1, I get a centripetal force of 29.58 newtons.